If you've ever played around with ChatGPT or seen those incredible AI-generated images or even heard about these wild breakthroughs in drug discovery, you've basically seen the work of one single fundamental idea. An idea that didn't just tweak AI, it completely rewrote the rulebook. Okay, let's get into it. We are talking about the transformer architecture. This is the engine behind pretty much the entire modern AI revolution. So, to really get why the transformer was such a game changer, we have to ask a question that honestly had researchers scratching their heads for decades. How does a machine actually understand what a sentence means? I mean, it all comes down to context, right? And for the longest time, AI had a massive context problem. And this problem, it was all about how older AI models were forced to think. They were basically trapped in what you could call a sequential bottleneck. I want you to imagine trying to read an entire novel, but you can only look at it through a tiny keyhole. That's exactly what AI was doing. Before 2017, the only way to do it was sequentially. The AI would read the first word, then the second, then the third, and all along the way, it's trying desperately to remember what came before. And as you can probably guess, this was just painfully slow and super inefficient. The models that worked this way were called recurrent neural networks, or RNNs for short. Now, they were pretty clever for their time. They used this kind of internal memory, a hidden state, to try and keep track of a sentence's meaning as it went along. But that core design, that one word at a time approach, well, it created two huge problems. So here were the two killer flaws. First, they had a terrible long-term memory. If you gave it a long paragraph, by the time the model got to the end, it had pretty much forgotten what the beginning was about. This is a famous issue called the vanishing gradient problem. And second, you couldn't parallelize them. You couldn't just throw more powerful computers at the problem to speed it up, because you had to process word one before you could get to word two, and so on. AI had basically hit a wall. And this, right here, perfectly sums up the difference. The old way, with RNNs and their slightly better cousins, LSTMs, was like being stuck looking at the world through that tiny pinhole. The transformer, it was designed to see the entire page all at once. Which brings us to this breakthrough moment in 2017. And it didn't come from some new supercomputer or a massive lab. It came from a single, beautifully simple research paper that proposed a totally radical new way of thinking. Now, what's really wild when you look at this is the time gap. For 20 years, from 1997 all the way to 2017, the smartest people in AI were all just trying to make sequential models a little bit better. They were making the pinhole a little bit bigger, but it was still a pinhole. Then, in 2017, this team from Google didn't just improve the old idea, they threw it out completely. And this was the title of that paper, Attention is All You Need. It was so much more than a title. It was like a declaration of independence from the old, slow way of doing things, a total paradigm shift. The idea was just beautiful in how audacious it was. The researchers basically said, let's get rid of that entire step-by-step, one-word-at-a-time thing. Let's throw it out and build a new system based only on a mechanism called attention. So what is this attention thing? How does it actually work? How does it let a model see the whole page at once and understand that rich, complicated web of context in a sentence? The magic trick at the heart of it all is called self-attention. Instead of passing memory down a chain, word by word, self-attention lets every single word in the sentence look at every other word, all at the same time. It dynamically figures out which words are most important for understanding its own meaning and creates direct connections, no matter how far apart they are in the sentence. Okay, let's break that down. Think of it like this. For every single word, the model creates three things. A query, which is like the word asking a question. Who in this sentence is relevant to me? A key, which is like a label on every other word saying, hey, this is the kind of info I have. And a value, which is the actual substance, the information that word can offer. The model just matches every query to every key to see which ones are the best fit. And then it blends their values together. And this happens for every word, all at the same time. It's brilliant. Right, so you might be thinking, hold on a second. If you ditch the one word at a time process and just look at a big bag of words all at once, how does the model know the difference between the dog bites the man and the man bites the dog? The meaning is totally different, but the words are the same. You've lost the order. The solution to this is just so clever. Before anything else happens, the model adds a little piece of information to each word called a positional encoding. You can think of it like a little timestamp or a GPS coordinate for every word. It doesn't tell the model what the word is, but it tells it exactly where it is in the sentence. First, second, third, and so on. So the model gets the best of both worlds. It can process everything in parallel, but still knows the original sequence. So now we've got this amazing new architecture that's super fast and can understand deep context. The next question was obvious. What can we actually do with it? And the answer, as it turned out, was pretty much everything. You see, the real power of the transformer wasn't just that it was one better model. It was more like a flexible blueprint, a new set of Lego bricks for building AI. And researchers very quickly realized they could take these bricks and reassemble them in all sorts of different ways to do different things. It was like a Cambrian explosion for new AI models. And this blueprint quickly gave rise to three main families. You've got your encoder-only models, like BERT. These guys are amazing at understanding context. They look at a sentence from both directions at once, which makes them perfect for stuff like Google search. Then you've got the decoder-only models, like GPT. These are built for generating new text. They read what came before and predict what should come next, which is exactly what powers chatbots. And finally, you have the full encoder-decoder models, like T5, which are great at transforming one thing into another, like translating a language or summarizing a long article. But the craziest part? It didn't stop at language. People realized you could treat almost anything like a sequence. So they started chopping up images into a sequence of patches and feeding them to vision transformers. Biologists started treating the amino acids in a protein like words in a sentence, which led to AlphaFold 2, an AI that solved the 50-year-old challenge of protein folding. It became this truly general-purpose tool for finding patterns in anything. So when we step all the way back, what's the real lasting legacy of this incredible idea? Well, it's actually about more than just a clever algorithm. The transformer showed up at the absolute perfect moment in time. Its parallel design was a perfect match for the incredibly powerful GPU and TPU computer chips that were just becoming widely available. And both of those things were ready to be let loose on the unimaginably huge datasets of the internet. It was a perfect storm, where the right idea met the right hardware and the right data. So at the end of the day, the true genius of the transformer wasn't just that it was smart, it was that it was scalable. It was the key that finally unlocked the massive potential that was sitting there, waiting, in all of our modern computing power and all of our data. It finally broke that sequential bottleneck that was holding AI back for so long. There's no question, the transformer has defined this entire era of artificial intelligence. It's taken us from slow, steady progress to these massive exponential leaps. And that really leaves us with a fascinating final question to think about. If this was the architecture that powered the last decade, what new idea, what new architecture is going to be the engine that defines the next?